Hi, I'm Max, and I'm going to present Multitask Soft Option Learning. Instead of learning one monolithic policy in hierarchical reinforcement learning, we learn a set of sub-policies, here shown in orange, and one master policy. To act, the master policy first chooses one of the sub-policies, which then outputs the action that is executed in the environment. Such a hierarchy offers several advantages. Firstly, sub-policies are a natural way of capturing and transferring knowledge between tasks, allowing novel ways of recombination. Secondly, temporally extended sub-policies allow more efficient exploration, reducing the numbers of required samples during transfer. In this work, we will be using the options framework to formalize such temporally extended sub-policies, which I will consequently call options. As a running example throughout this presentation, I will be using the famous taxi environment. The agent, shown here in the top left square, needs to first pick up a passenger, here in the blue square, and subsequently drop it off at another location. Pickup and drop-off are always at one of the four color-coded locations, red, green, yellow, and blue, allowing for a total of 12 different tasks. One important question is how we can find and learn good options. In this work, our goal is to learn a set of options from a distribution over tasks, for example, the 12 different pickup and drop-off locations in the taxi environment, by optimizing for option policies which are useful across multiple tasks. The idea is that options which are useful across many training tasks are also more likely to transfer well to new tasks from the same or a similar distribution. On this slide, you can see a schematic representation of learning one set of options across two tasks. In the first task, the passenger travels from yellow to blue, and in the second one, they travel from green to blue. The set of options which is shared across both tasks is shown in the middle, with the color indicating to which location the agent is moved by each option. So in this case, the master policy for task 1 would first pick option 3 to travel to the passenger on the yellow square, followed by option 4 to reach the blue square. Of course, this exact solution is just an example of many possible ones. Furthermore, none of this is given to the agent at the beginning of training, and the goal of our training algorithm is to learn such options which are reusable across many tasks. Unfortunately, attempting to simply optimize a set of shared options across multiple tasks will run into three challenges. Firstly, it is easy to get stuck in a local optimum. Secondly, sharing the same set of options across tasks assumes that exactly the same options are required across all such tasks. And lastly, for better exploration, we need to encourage temporally extended options. More details on this last point can be found in the paper. To better understand the first challenge, imagine the following situation in which 3 of our available 4 options have learned to reach the yellow square, and 1 option has learned to reach the blue square. This is a perfectly acceptable solution on task 1. Unfortunately, we are unable to solve task 2 as we cannot reach the green square. Importantly, we also cannot modify any of the yellow options, as master policies on other tasks, for example task 1, will rely on their behavior to reach yellow. If we were to modify any of the first 3 options, we would likely experience our stark drop in performance on task 1 or similar tasks, preventing us to change those options using greedy optimization algorithms, like for example gradient descent, which in turn leads to the observed local maximum of insufficient option diversity. A second multitask challenge arises when different tasks require slightly different goal locations. Imagine, for example, that for one task, the blue pickup or drop-off location were moved slightly. This could not be solved by just one fixed option and would instead require 2 different options despite the similarity of both tasks. Furthermore, if such a shift were to occur during transfer, our trained options would not be able to solve the new task at all. Next, I will outline the idea behind soft options. The idea of soft options is not to share the exact same set of options across all tasks, but only softly regularize them against one another. On the slide, you can see the task-specific options, also called posterior options Q, at the top and bottom, while the prior options in the middle are shared between all tasks. Each set of posterior options is regularized against the jointly learned prior by minimizing the KL divergence between them here indicated by the springs. We refer to the sets by prior and posterior due to the close relationships to the RL's inference literature, which sees task-specific rewards as likelihoods, resulting in task-specific posterior policies different from task-independent priors. Importantly, here we also learn the prior jointly with the posteriors. Furthermore, during transfer, we would initiate the options using this learned prior. In other words, the prior serves as our prototype option. Mathematically, we use standard RL algorithms, in our case PPO, but now optimize a regularized reward, which penalizes high KL divergences between the prior and all posteriors. As we are using the option framework, we consequently have prior-posterior policies for the intra-option policies, the master policies, and the termination policies, which are required for temporally extended options. So how does this help us overcome the aforementioned challenges? For the local optimization maximum, imagine again the previously discussed situation. Because now we are using soft options, we can change one of the local yellow options on task 2 towards reaching the green square, allowing us to now successfully also solve this task. Of course, this will now introduce regularization costs between the new posterior and the prior. As a consequence, the jointly learned prior will adapt and will now represent a policy in between the two different posteriors. Importantly, this means that now on task 1, the master policy will pay this additional regularization cost if, but only if it chooses to use option 2 to reach yellow. Consequently, it will learn to only use option 1 and 3 instead, thereby freeing up option 2. In other words, master policies prefer to use specialized options which are consistent across all tasks because this minimizes the KL regularization term, which they have to pay. This means through the regularization, option 2 can now equalize across all tasks, leading to the same set of options across all tasks despite only soft regularization. Regarding the second challenge of slightly different goal locations between tasks, it is easy to see how allowing options to locally adapt to the task allows us to capture multiple different but similar behaviors with the same option. This applies both to training and even more importantly during transfer, as applying hard, i.e. exactly shared options to a changing task distribution can lead to highly suboptimal performance. Thank you very much for your attention. More detail about the algorithm, as well as experiments and quantitative results, can be found in the paper.